So guys, welcome back. Today we continue with clustering, and just added a couple of slides. In fact, here we'll describe the K-means algorithm. In fact, so what is K-means? In fact, it represents the nodes in the graph as vectors. Here, vectors are in fact vectors of coordinates. So the clusters, for example, in two means clustering, the clusters P and Q may have centroids or centers. Let's say CP and CQ. So what are we willing to do is to minimize the total square distance from nodes to those centroids. The centroid is the average, in fact, its coordinates are the average of the coordinates of the items in the cluster. So when you say you write this means the cardinality. What is the cardinality? Cardinality, it means the number of items in the set. Cardinality. So if you take the set P, I mean the cluster P, the cardinality is the number of the items in the set P. Okay, so you sum up all the coordinates and you divide by the number of items in the cluster, so you get the coordinates, in fact, of the center. So, for example, in two means clustering, my objective is to find the two centroids coordinates, and for that we do minimize E, which is the sum on all the items in P of the squares of the distances from every point in P, AI, which means here represent the coordinates of the point I, to the centroid, CP. Okay? And the sum on all the items in Q, in the cluster Q, of the distances from AI to the centroids, CP. Okay, so you are kind of minimizing the sum of the squares of the distances here. So, of course, the vector AI may or not represent, in fact, the physical location of a node. It may represent something else, for example, the weight or something like this. So, the clustering objective E is not, in fact, restricted to Euclidean distances. It might be, in fact, not Euclidean, let's say, geocoded distances. I mean, real distances, or in fact, road distances, travel times, stuff like this. Okay. Sometimes there is a variation we call kernel K-means, which is more general. So the more general kernel K-means algorithm, in fact, works entirely with kernel matrix K, that in fact assigns inner products Kij's, which are the products of these vectors AI by Ij's. And the distances and means are computed from the weighted K matrix. And the distance measure E will also be weighted to improve the clusters P and Q representative. So now let's talk about what we call the Laplacian matrix. If you remember last time, before we started lecturing, we talked about the Laplacian matrix of a graph. So the first step is to define L, which is in fact ATA, where A is in fact what we call the incidence matrix. This is an M by N incidence matrix of the graph. Of the diagonal, the ij entry of ATA is -1 if an edge connects to node I, connects nodes I and j. And the diagonal entries make all rows sum 0. Then at every diagonal, what you have the degree of the node R, the number of edges into the node R. Okay, so with all weights equal to 1, in the most simple case, in fact, ATA gives what? The degree matrix minus the edge in C matrix, as we've seen last time. So it's in fact D minus A. Okay, but if you add weights now, with the edge weights in C, you may have weights, which mean every edge has, for example, a cost. C is more general for cost. Okay, it could be a distance, or it could be a time, a price, and the edge weights in C can be conductances or string constants or edge lengths, if you think so. So they appear on and end of the diagonal of what we call ATCA. So this is a small modification in the Laplacian matrix. So you have ATCA, which is D minus W, which means node weight matrix now, minus the edge weight matrix. And of the diagonal, the entries of minus W are in fact minus the weights Wij's on the arcs Ij's. In fact, the diagonal entries D is still made all of rows zeros. This is a space I missed. Right. Okay, now let's talk a little bit about what we call the normalized weighted Laplacian. So this is just a small modification. For the normalized weighted Laplacian, what we do is to multiply ATCA, and here these are the weights, on the left and the right by what we call d to the power minus half. And this way preserve the symmetry. So what happens is that rho I and column j are divided by the square root of di and square root of dj. So the ij entry of ATCA is divided in fact by the square root of di dj. Then the Laplacian matrix has di over di equals 1 along its main diagonal. So if you start with a normalized Laplacian, this is normal Laplacian. We took the weighted Laplacian, which is here, ATCA, and you multiply it from the left and right by d to the power minus half. So we got what we call now I minus n. These are the weights we added, and ij's, normalized weights, which is wij divided by the square root of di dj. So if you start from this matrix, which is ATCA, which is given this way, and in this small example, we have a triangular graph where n equals 3 nodes and m equals 3 edge weights. We call them C1, C2, C3, or if you wish, you can call them W12, W13, W23. Okay? So in fact, these are the weights. And of course, it means that W13 is also W31. Okay? It's the same weight on undirected edges. So this is the D minus W, or the weighted Laplacian. And if you want to compute the normalized Laplacian, you get something like this. Okay? So after you use that formula that was presented here, d to the power minus half times ATCA d to the power minus half, you get the following normalized Laplacian. Okay? The advantage is that this normalized Laplacian takes into account the weights, and it gives you normalization on, let's say, on the size of the entries you have. Okay? Of course, this is n to n with a subscript f32. So the normalized Laplacian is equal to n, which is I minus n. It's like a kind of, in fact, a matrix, a correlation matrix in statistics with unit diagram, as you can see. Okay? And it has mainly three properties that are crucial for clustering. First of all, this L is symmetric, positive semi-definite, and you know how much we love that, with orthogonal eigenvectors and eigenvalues. And this is wonderful, as you know. Okay? Eigenvalues positive, more than this. So the eigenvector for a equals 0 is given this way. So square root of d1 till dn, and you will get Lu, which is given by this normalized Laplacian matrix multiplied by 1, which gives you this. This is for a one vector, a vector with all entries equal to 1, which gives you 0. And the second eigenvector v of L minimizes, in fact, the Rayleigh quotient on a subspace. So the corresponding eigenvalue would minimize the Rayleigh quotient with the condition that x u equal to 0. Okay? So these are some properties of the normalized weighted Laplacian. So normally with the K-means, we prefer much more to work with a normalized weight Laplacian than it is with weighted Laplacian or with the normal Laplacian. So that's it. So as promised, I will add a small example on how to implement that and how to run things.